Chicago, the Windy City, who will talk about a finite elemental analysis, FEM analysis, of stabilizing skin for osseointegration.
So good afternoon again. You probably realized from a little while ago my lab is mostly about steering. We do control of artificial limbs. However, it's filled with all these young, bright biomedical engineering students, and I do have a passion for osseointegration and excited about its promise. So we had one project that we could focus on with mathematical modeling that we thought would add a little bit to the science. And this is really my student's work, Vasu, who is now off in India vacationing. And so I'm going to present his work on making a finite element model to look at the skin interface. So again, we don't have to go through all the problems of sockets. I hate sockets, and I'm very excited about direct skeletal attachment of prostheses. The big challenge, as Ricard pointed out this morning, I think, though, is really the skin interface. You inherently have some type of an open wound, which nature abhors an open wound, and skin tries to stabilize it in some way or get around it. And so there's a significant risk of infection. However, if you look at the big labs around the world that are addressing this issue, they're all doing it somewhat the same way. You need to stabilize the skin so that it's not floating around and having a big open gap for the infection to come through. They do it in different ways. Dr. Brannemark's group is taking the skin and adhering it very closely to bone to get a seal around, and the ITAP group has their flange with hydroxyapatite, which they seal the skin to, and the University of Utah has a porous titanium that they seal the skin onto. This is all from published material. And so they're similar in that they're trying to get the skin to seal around a firmer material, be it bone, metal, or another type of titanium. So we thought we would take a look at how this seal needs to work, or how we can look at the stress of the skin around such a firm material interface. And our hypothesis was that if you had a larger surface contact area, you might be able to actually take some of the stress away from the skin right where the abutment comes out, or at the skin to percutaneous material interface. So we built a 3D, I keep saying we, Vasu built a 3D finite element model of a osseointegrated transfemoral residual limb, a single bone coming through. And then we varied the amount of pressure that we would stress the skin and looked at its effect as it came to the area where the stabilizing flange or bone or abutment came out. And we varied the size of the force as well as the location of the force. Now this is the model. Essentially you have the residual limb, you have a big rod of metal coming out, and then just for the ease of modeling, we had these little layers, these cylinders around it that could be made to either be muscle or bone. So we, and this little area up here is really the interesting part. So you could have, in one model, have this section 1 be bone only with the adhesion of the skin only to this area right here, and then turn the rest of them into muscle magically with your model. Or you could turn 2 layers of it into the bone or solid material, 3, 4, so on. And it doesn't matter how long this all went down. This is just for modeling purposes. What really mattered was you could imagine this being a flange or being bone. But we looked at this skin region as it adhered to a very stiff material. And here's lots of nice engineering parameters that Vasu used if anybody's worried about how stiff the bone was or the skin, muscle, etc. This is the finite element model. It's actually quite high density thanks to modern computers. And you can get a visual of if we imagine a pressing on the thigh and giving a shear force down. This is the area where the force was applied to the residual limb, and then we looked up around the abutment at what forces resulted. So now we're looking at the top of the residual limb. This would be where the metal part would be sticking through. Imagine down here some type of force, and this is the pattern you get if you only have 2 millimeters of skin adhering to the bone or stiff material of a flange. As you make the bone or metal flange bigger, you see that a very bright high intensity line where all the shear is absorbed right at the edge of whatever material you have, and then a lighter dissipation as it goes out. And here's 6 millimeters and 8. The other interesting thing to note is this is the skin right next to whatever the percutaneous material is, to the abutment. And as you go to a larger ring, you see that there's less and less shear force pulling at that skin. So it is relatively stabilized. And when you look at it with a nice little plotted graph, this is the take-home slide of the day. With only 2 millimeters of adhesion, you see that you very abruptly accept most of the force, and most of the force in the skin is right at the edge of that 2 millimeters, and then it comes down lower, close to the abutment. But as you add more material, stiff material underneath it, the peak goes out, but also you get a relatively less force pulling at that area of the skin right next to the abutment, and you're stabilizing underneath it. So the question is whether you could, if you could keep, I guess, 2 or 4 millimeters all the time. Those are still relatively small numbers compared to their peaks, but they're not insignificant. And if you have any kind of little lip around the edge where you don't get your full 2 millimeters, then you're at risk of opening up. So it advocates for a broader brim around the device, but it does plateau as well too. So you're getting to, as you go from 2 to 4, it's really abrupt. You go from 4 to 6 to 8 millimeters, it's less dramatic, but still significant. And these are the percent decreases of stress that you see right at the skin interface as it gets bigger. Now, I showed you just for one force. The fact is that this is a linear model. And so for this model, it doesn't really matter how much force you apply. But do please remember this is a mathematical model and is simplified in many ways. We're not using viscoelastic fluids modeling of skin. We're using a simple stress strain model of skin and bone. So there could be considerable error or difference there. We are adhering the skin infinitely tight to whatever our little boundary condition is. And we unfortunately have no data as to when it would rip off. And so one of the things we'd like to look at next is if you have a high enough force to actually start ripping the skin, how does it propagate? So I think take it all with a grain of salt, since it's a mathematical model that has not got any decent data to validate it. But it is based in good material properties and I believe good mathematics to give us some insights as to how the skin behaves when it's attached to a firm collar around an abutment. And that's it. Thank you. Any questions? I probably won't be able to answer them, but you can try.
Thanks a lot, Todd.
Okay.
Please stay.
Okay. Do I have any engineers out there to quiz me?
Yes. We have one half engineer.
I don't know if he counts.
No, but I think this fits a little bit in what we're trying to do clinically. So maybe that can guide us in the area that we would like to have stabilized, and we use a bone grafting technique to get a little bit a bigger area, but we just play by by heart, and here you have at least some figures that can say, okay, this is the area of the ring that we need to attach for certain forces. Or what would be great is we could evaluate sort of what are the forces acting from when the muscles are pulling the skin, and add those into your model, because that would verify your calculations, and that would help us to say, okay, that is a relevant area to go for when we do the surgical approach. Can you do that?
So with this model, we could, however, because it's linear, so this would be some small force down here that you might get from skin having a stress on, muscle having a stress on skin. And actually this force was the highest force we could possibly imagine putting on, and that was if somebody had their entire weight at 45-degree angle on their residual limb. This was the highest force, and it turns out the force we picked doesn't matter to a large extent because it's such a linear model. Yeah, there's some compression and deformation issues, but it's surprisingly linear. So we're looking at, with this model, pretty high forces as well. I do think, though, that the way you're getting extra cortex or bone to adhere around the abutment makes a ton of sense and is validated by this model, and also that, you know, up to 6 to 8 millimeters should be adequate.
I'm Dr. Berlin. Sometimes you see a clinical problem where the skin around the abutment penetration area goes into necrosis, and then sometimes we used skin grafts and we mesh them, and sometimes we can see that they heal. Do you have any kind of viewpoints of how that could work out, and if there's any way you can look at that in your model?
Well, with that parameter, what we would be looking at is a lot thinner skin. So the split thickness skin graft, I don't know the numbers, but I'm sure it's less than half the thickness. And it's a little stiffer material. But I think what we would find is this similar pattern of wherever the hard material ended is where all the skin force would be. And my concern with the split thickness skin graft is that it's a less resilient skin to take that force in terms of, but that goes beyond this model. That would be going on to, my word, beyond the physiology of the skin itself. So I don't think I can shed a lot of light with this model.
Okay. Thank you.
Thank you.
So Todd, in dentistry, this type of approach to calculate how stresses are distributed around the abutment per mucosal implants, I believe has meant a lot for the design of the actual mucosa penetrating implant. Could you anticipate something similar here?
Well, I imagine that science is far more sophisticated than what we've done, and includes more layers of tissue than just skin, because the mucosa has its epidermis, if you would, as well as some other structures under it before you get to the bone. And so it's, to an extent, more complex than what we are doing in the prosthetics world. But the insights, I should have our student or the next one look at that modeling, because I'm sure it's much more complete than this, and it would have actually some data.
Yeah, because this must be really the first type of data around.
I think,
yeah.
Yeah, I think
yeah.
for the amputee model in any case,
yes.
it's a very, very simple first stab.
Thanks a lot, Tom.